Ready, everyone, we'll get started. So welcome to another review session. Happy Wednesday. It's like our first full week of school this week, it feels like. So we will kick it off today with a few announcements. I don't think I have too much for y'all. You should be able to see your quizzes tomorrow at like 5 p.m. or so, depending on what you got done. So you can look out for that, and then your first exam isn't for a couple weeks, so you still got some time, but that is going to come up sooner than you think. So just keep that on the back burner as we move forward. Other than that, I don't think I have any announcements. So yeah, are there any questions for me before we get started? Alrighty, what would we like to see today? Grades, yeah, absolutely. Alrighty, so when we look at net ionic equations, what is this for? Like, what kind of reactions are this for? These are for precipitation reactions. And what does it mean to be a precipitation reaction? What's forming in a precipitation reaction? Yep, so this is going to be solid formation. All right, we're going to call this an insoluble salt. Yep, so the example that they give in your slides is 2Ki aqueous plus Pb NO3 2 aqueous forming PBI solid and 2 KNO3. Oh. So you have potassium iodide and lead nitrate in solution in an aqueous solution, forming lead iodide solid and potassium nitrate still remaining aqueous. All right, so this is our overall chemical equation. Okay, we can split our overall equation into its ion forms. So if something is aqueous, what does that mean for the ions? Is it looking like potassium iodide, or is it looking like potassium and iodide? Potassium and iodide, right? They split apart. They're no longer a compound. They are their ion forms. So we have how many potassium ions? 2. So we have 2K plus. Those are aqueous. We have 2 I minuses. Those are aqueous. What about lead nitrate? What does that look like? 1 Pb. What's the charge on lead? 2 plus. Right, and we know that because NO3 minus is a polyatomic ion. I do believe that will be given to you on a chart, so you can check it. But we have 2 of those NO3s, so that means we need 2 for our lead. So we have 2 NO3 minus aqueous. And then what about PBI? Does that split into anything? Sorry, this should be I2. No, right? This is a solid. That means that we can no longer break it apart. It has to stay in its solid form. So this stays as PbI2 solid. And what about potassium nitrate? What happens there? That splits apart because it's still aqueous. So that's going to be 2K plus aqueous, and this is 2NO3 minus aqueous. Right, and this would be our ionic chemical equation, where you have everything going on in the reaction in your chemical reaction, right? You split everything that can be an ion into its ions. Okay. So once we have our ionic chemical equation, then we can write our net ionic equation. Any questions on how we got to the ionic chemical equation? That makes sense how we split our ions. Then we get to our net ionic equation. What happens when we write our net ionic equation? What are we doing? Right, we're canceling from both sides what looks the same. So what looks the same? So the 2NO3 looks the same. We have 2 NO3s on our left and 2 NO3s on our right, and they're both aqueous, right? They have to have the same sign, or the same phase, and they have to have the same, right, ion composition. All right, so we have NO3 minus, what else? Yep, the potassium is the same too. Yep. So those are the same. So we can cancel these out and these out. So what does that leave us with? That leaves us with iodine, and that leaves us with lead, and that leaves us with our solid lead iodide. So we then have 2I minus aqueous plus Pb2 plus aqueous going to PbI solid. And this becomes our net ionic equation. This is telling us the chemistry that's actually happening in our solution, right? The potassium and the nitrate ions, they're in solution. They're just hanging out, having a jolly good time. They're not doing any chemistry. Your lead and iodine ions, on the other hand, when they're in solution, when they come together and they make contact with each other, they now form their lead iodine solid and they fall out of solution, forming that precipitate. So that's really what we care about. This is the chemistry going on, right? And that's what we care about. So then that ionic equation is just telling you the important stuff, right? That's telling you the meat and potatoes. Okay, any questions on how we get there? Yep.
We bought this charge up there on the solid, but that's probably gonna make the question insignificant, but you don't put charges on like solids, you just bring it down.
You just bring it down, right? So the charge is coming from, right, we have PbI2. The charge is coming from how many ions we have in your compound, right? We know that we have 2 iodine ions, or 2 iodine atoms. What is the charge on an iodine atom? It's -1, right? We saw that in our ionic equation, it's -1. What is the charge on our Pb ion? 2 plus. So we need the 2 plus ion, that stays the same, and then the -1 from our iodine stays the same. So we need 2 iodines for every 1 lead ion that we have. So the charge is in the compound. Yep. Yep. It should. Yep. So as long as your overall chemical equation is balanced before you begin, then your net ionic equation will also be balanced. Yep. Right, and we can see that too. You have 2 iodine ions on your left, 2 in the solid compound, 1 lead, and then 1 in the solid compound.
Don't balance first. He said do the break it into the net ionic and then balance it out.
Either one will work. Either one will work. Because your net ionic equation, right, you don't need to, if you just balance your net ionic equation, you're not balancing the other stuff that you don't need. If it comes balanced, then that's fine too. It also helps to not be balanced because then you don't have to worry about doing a situation where you accidentally put a subscript of a 2 instead of a coefficient of a 2 or something like that. Yep. Either one, whatever you prefer. You could always balance your net ionic equation and go back and balance your overall equation too as a check. Okay, questions here? Okay, let's practice one. Right, so for this one, we have nickel chloride and potassium phosphate forming nickel phosphate solid and potassium chloride aqueous. Okay, so I want you to write me the net ionic equation for this reaction. Is that something we want to try on our own? Yeah, okay. Work with people around you too. Alrighty, did we get a net ionic equation? What did we get? Mm-hmm. Do you have a charge? Mm-hmm. And what else?
Yeah.
Yep. Charge? Absolutely. What does that form? Beautiful. Perfect, right? So you have nickel 3+ and phosphate 3-, forming nickel phosphate. Where that came from is that you had nickel 3+ aqueous, and then you have 3 chloride- aqueous ions. You have 3 K+ and a phosphate 3- ion. You have your solid, and then you have 3 K+ and 3 Cl-. Okay, so as we cancel that out, then we have chloride, potassium, potassium chloride. And so we're left with the nickel and the phosphate. Alrighty, any questions there? Okay, how do we feel about predicting the products if something's going to be soluble or insoluble? Do you want to do a little practice with that? Sure. Okay. So I want you to okay, so I want you to predict the product and then tell me if it's insoluble or insoluble. Yep.
You gotta have the like soluble and insoluble chart.
Yeah, you'll be given the solubility chart on your exam. I don't know how to display the question in that, so I think it's in your slides. It should be in your slides. Okay, did we predict a product for ammonia and carboxide? Yep, for A. It should be soluble. Yep, and what's the compound that gets formed? Say if it were to be solid, what would it form? It form NH4, 2, CO3. Yep, right, because we have a 2 minus for our CO3 ion, and then we have a plus for our ammonia ion. So we need 2 ammonias for every 1 carboxy. Okay, but this is going to be soluble. Anything with NH4, anything with ammonia will be soluble. That's one of the non-exceptions. Yep.
So we don't have to put AQ.
You would, like, if you're gonna write it out in a reaction, you put AQ. We're just predicting products right now. Okay, silver and chlorine. What product is formed? Yep, this one's just AgCl. You have a +1, -1, so you don't need any subscripts. And what is the phase of this one? This one's insoluble. This is a solid. Chlorine is usually soluble, but it is insoluble with silver, mercury, and lead. But you don't need to know that. You just need to know how to read the term. Okay, what about Ag in sulfide? What compound is formed there? Perfect. We have silver sulfide. And what is the phase? This one's going to be insoluble. Sulfide ions are usually insoluble, and this is not one of the exceptions. So this one will remain insoluble. Okay, and then what about aluminum chromate? What compound is formed? Beautiful. And what is that? That's solid. This is insoluble. Chromate is usually insoluble, and the aluminum is not one of the exceptions for it. Okay, what questions do we have about reading that solubility chart? Does that make sense how you follow it? Yeah, okay. Alrighty, any other questions that we have?
Whenever you're balancing an equation,
Mhm.
is there like a better way to go about it? Or kind of just
Yeah, so let's do one together and I'll kind of walk you through what I would do. So if we have something like a combustion reaction, right? We have, what's a hard one? Let's do C2H6. So I have C2H6 and I'm doing a combustion reaction. What does that mean?
hydrocarbon, oxygen, and you're gonna get water in carbon dioxide.
Beautiful, right? So in a combustion reaction, we have a hydrocarbon. It's just carbon and hydrogen. Technically, you can have a combustion reaction with something that has carbon, hydrogen, and oxygen. It can even be nitrogen and hydrogen, but for the sake of this, right, a combustion reaction means that something is burning with oxygen. And we're forming carbon dioxide and H2O. Okay, so when I'm balancing an equation, I always go left to right. So when I look at my first atom, I have carbon. I see that I have 2 on my left and I have 1 on my right. So I'll put a 2 in front of carbon. I then have 6 hydrogens and 2 on my left and 2 on my right. So I'm going to put a 3 in front of my hydrogens. I automatically know that that 3 in front of my hydrogens is going to cause me to have an odd number of hydrogen or odd number of oxygens on my right-hand side. So I stop there and I immediately go back and I say, okay, I'm going to put a 2 in front of my original compound that I started with. That now means I have 4 carbons. So instead of a 2, I'm going to put a 4. And instead of 6 hydrogens, I now have 12 hydrogens. So instead of a 3, I'm going to put a 6. That now gives me even number with my carbon dioxide oxygens and an even number from my water oxygens. So then I can combine those. So I have 8 from my carbon dioxide and I have 6 from my water. So I have 17 total oxygens on my right-hand side. And so then I know that I need to divide by 2. So I have 7 oxygens on my left. And that's where I start. And that's where I would go through one of those. Okay, so I think it's easiest to go left to right until you obviously see that something is wrong. A lot of the combustion reactions, if you see an odd number in front of your hydrogen, nix it and immediately go back to multiplying by 2 for that front one. I'll give you a hint for a combustion reaction. If you see anything like with an even number of carbons, you can almost always multiply by 2 to start off. So anything that's like an alkane like this. So if you have C4, what is this? We'll do I'll show you C3H8, an oxygen. Right, your even number of hydrogens, this is going to be 3. It doesn't matter what it's in front of your carbons. Oh, I guess put it different. Your even number in front of your water molecules will always make those oxygens even. So you don't need to worry about it. You're not going to change the coefficient in front of your hydrocarbon. But if we looked at C4H10, right now we still have to multiply this by 4, but now we have 5 originally. So whenever you have that odd number of hydrogens, you can always go by 2. So this turns into 2, 8, 10. Right, so that even number of carbons, and then odd number when you divide by 2 for the hydrogens. And that's for combustion reactions. So then, again, if we just did something like my first reaction here, I'm going to say I have right work left to right. So I have 2 nitrogens on my left. I have 1 nitrogen on my right. Multiply that by 2. I have an even number, 6 of hydrogens on my right. I have 2 on my left, so I can multiply this by 3, and that gets everything happy. So I think working left to right is the best. And then the other thing that you do is you work so that you balance the thing that's by itself first. So your oxygens appear in both the carbon dioxide and the water. So I'm not going to start with the oxygens on my combustion reaction, right? That appears in two different compounds. I have to first manipulate and make sure that the thing that only appears in one compound first is balanced instead of trying to manipulate everything all together. Let me see if I have an example of that. Right, like right, if we have sodium and water forming sodium hydroxide and hydrogen gas. I'm not going to start by balancing my hydrogens. My hydrogens appear in both compounds on the right-hand side in my products. So if I start messing around with the water, that's kind of going to screw up my nitrogens, or not my nitrogens, my sodiums here. So start with the thing that only appears in one compound. Start with the sodium first. That's already balanced, so that's good to go. Right, you're going to move on to the oxygens. Your oxygens are balanced, so that's good to go. So now you have to start with your hydrogens, right? Check the things that only appear in one compound first. In this case, we have 2 hydrogens on our left and 3 hydrogens on our right. So I would probably multiply this by 3 first. Now I've messed up my oxygens that only appears in one compound. So I can go over and change the 3 there. What did that change next? The sodium. So what do you have to change about your sodium? Multiply by 3. All right. We now have 6 hydrogens on our left. And how many hydrogens do we have on our right? 5. Can we do anything? Not really, right? We can't multiply by 2 in the H2. That'll give us too many. So what do we do if we can't have an even number? What do we change first? We change the hydrogens, right? So let's change this to 6, right? Using an odd number gave us an odd number. So let's make it an even number. Let's multiply it by 2. If we multiplied that by 2, what do we have to else? What else do we have to change? Yep, this turns into 6 sodium hydroxides. And what does that mean for the sodiums? That also has to go up to 6. How many total hydrogens do we have on our left-hand side now? 12. How many do we have on our right-hand side? We have 8. 6 from our sodium hydroxide, 2 from our hydrogen gas. So we can put a 3 in front of our H2. Okay, do we see like that thought process behind all of that? Whenever you get an odd number, instead of like trying to make a fraction, I just multiply everything by 2. Because worst case scenario, you just reduce it down. Did that help your question?
Yeah.
Okay. Anything else I can help y'all with tonight? How are we feeling about the material so far?
Out of the quiz.
Are you able to see your scores first? You scored. Okay, that should be released tomorrow. Okay. Anything else y'all want to see? Anything? Do you want to do a little bit of like combustion with percent composition and stuff? Where do I?
Well, no, wait.
It should be tonight or first thing tomorrow. Yeah. Yep. Is that a yes to the percent combustion stuff? Okay. Okay, so we have a hydrocarbon is fully combusted with excess oxygen to yield 23.118 grams of carbon dioxide and 4.729 grams of H2O. I want to know what the empirical formula is. All right, so if we were to write out a just general combustion reaction equation, we have C in X and H, Y, because we don't know what those subscripts are yet. We have oxygen that it's burning with, and it's forming CO2 and H2O. Do you want to try this question on your own? Or work through it together? You want to work through it together? Yeah, absolutely. Okay. So, right, the big thing to know about a combustion analysis question or finding the empirical formula question is that your carbon only appears in one product, right? It only appears in the carbon dioxide. And then your hydrogen only appears in your H2O on this product side. So that means that any carbon dioxide that's collected, all of that carbon came from the original compound that you're burning, and all of that hydrogen came from the original compound that you're burning. So if we collect 23.118 grams of carbon dioxide, can we get to the grams or moles of carbon that we started with? Yeah, right? Because we know that the carbon within this gram, right, the carbon dioxide grams contains the carbon grams that we're looking for. How do we use that, or what do we need? Yep, we need the molar mass of carbon dioxide. I'll tell you that that is 44.01 grams of CO2. And that's for how many moles? Just one, yep. And how do we get to moles of carbon? Set up a mole ratio, perfect, right? So for every one CO2 molecule, how many CO2 or how many carbon atoms do we have? Just one, right? There's only a one, right, phantom subscript for CO2. So for every 1 mole of CO2, we have 1 mole of carbon. And then how do we find the total moles of carbon? We just divide 23 by 44. So that gets us 0.5258 moles of carbon.
So what would you multiply by Avogadro? Like, what are you looking for when you do that?
So Avogadro's number, that's a great question. Avogadro's number is 6.02 times 10 to the 23. And this is atoms, molecules, anything else, right? Compounds, whatever you need. That's when you're looking for how many atoms something has, right? So if I said how many atoms of carbon is that, then you would multiply by Avogadro's number. But that doesn't matter here for the empirical formula because we just need a molar ratio between the two of them. Right, that unit on Avogadro's number can change. That can be water bottles, shoes, right, anything like that. So that's always changing, but it's always equal to 1 mole. So you have to be in moles first before you can use Avogadro's number. Yep.
Why is the final answer moles of carbon? Like, where does the oxygen go? I guess I don't understand that.
So the oxygen here doesn't matter because what we're saying is that the hydrocarbon is fully combusted with excess oxygen. So the oxygen is just in plethora. It'll always be extra. We're just looking for that original hydrocarbon, which is just composed of the carbon and hydrogen. So the oxygen is just there as like a stand-in. There are some questions where the thing being burned has oxygen in it, and then that comes into play. But that's like a challenge question. Good question. Alrighty, so we are in moles of carbon. What do we have to do to get to moles of hydrogen? Yep, so same thing, but we're just gonna use the water molecule instead. So we have 4.729 grams of H2O. 1 mole of H2O is 18.02 grams. And then I think we said that we had to multiply it by 2, and that's correct, right? Because for every 1 mole of H2O, we have 2 hydrogen atoms. So 1 mole of H2 is 2 moles, I'm sorry, of H2O is 2 moles of hydrogen. Right, do we see where that comes from? The ratio between that? Okay. So then this gets us to 0.525 moles of hydrogen. Okay, and what do we do? Yep.
You know, like, when you stop, like, writing numbers.
Feel. Usually for the original, right, I see that there are 4 sig figs in my original mass for the hydrogen, so I give myself 4 sig figs for the number of decimal places. If I see 4 sig figs, usually, or sometimes I will give myself an additional sig fig and then I round at the very end. So I just go based off of the mass that's, or like the original number that's given to me. So I could, right, the carbon dioxide has 5 sig figs there, so I should have given myself 1 more if I was following my rule. All right, so then once we have our moles of carbon and our moles of hydrogen, what do we do from there? Perfect, right? So we need to find a ratio between carbon and hydrogen. And we do that by dividing by the smallest mole, number of moles that we have. So in this case, that's going to be the hydrogen. And this comes out to about 1, and this is equal to 1. Right, it's 1.001, so 1.00 is close enough to 1. And that will give us our ratio of carbon to hydrogen. Are those whole numbers? Yeah, right. So that's not a decimal. It's not like 1.3. It's not 2.7. It is 1 to 1. That's good. That's good to go. So what is our empirical formula for this hydrocarbon? It's just CH. Yep. Okay. The empirical formula is our most reduced version of that compound. Right, when you were looking at, go ahead. Yep, so we have, right, the carbon and the number of moles of carbon and the number of moles of hydrogen. In order to find that ratio that's needed for our empirical formula, we need to divide by the smallest number, because that will give us, right, 1 as our ratio as a starting point for the smallest one. And then there would be another ratio for the carbon there. In this case, we have, right, the 1-to-1 ratio, so nothing is really mattering. But more often than not, your hydrogen will be your most abundant, right? So you'll have a large number for that one, and carbon or oxygen, whatever's in your compound, will be the smallest one. Okay. Does that make sense? Right, that establishes the ratio between the atoms. Okay, so then the empirical formula is your smallest ratio of that compound. So if I were to say that the molecular formula not the molecular formula, the molecular weight, excuse me. What is the molecular formula? How would you solve that part of the question?
Use your moles that you found in your carbon.
We can do something easier than that. Right, the molecular formula is just a larger version of your empirical formula. It will still have the same ratio of carbon to hydrogens. There's just more stuff in the molecular formula. So for our empirical formula, what's our molecular weight or our molar mass for carbon, hydrogen? 12 and 1, so about 13.03, right, if we're rounding? 13.02 grams per mole. It's still a ratio. So we're saying that our molecular formula we know is bigger than our empirical formula. So we know that 39 grams per mole, right, is 13.02 grams per mole. So what is that ratio? Or what is that? Yeah, I guess ratio. 3, right? So our molecular formula is 3 times as big as our empirical formula. So how do we get to our molecular formula? We multiply all of our subscripts by 3. So it'll be C3H3. And that would be your molecular formula. Right, you just need to take your molecular mass of your molecular formula divided by the molecular mass of your empirical formula. It should be a whole number ratio, right? It should be a multiple of 2, 3, 4, 5, whatever it is. So then all of your numbers, if they're already in a whole number, it should remain a whole number. Any questions there? Okay, does that make sense for empirical and molecular formulas? Does that help with those? Anything else y'all want to see from me today? Yep.
Question. So when you do the net ionic equation.
Yep.
If it's a solid, you can't break it up.
You cannot break it up, right? Yep. If you give me a second, I can sign into the homework and I can tell you. Mm-hmm. What assignment and question are you looking at? Okay, so are you looking at like B and C? Yeah. So when we look at those, this is the one I'm looking at. Right, the only thing you can break up in your net ionic equation are aqueous solutions. So when we're looking at aluminum hydroxide, can we break that up? No, right? This has to stay as AlOH3 solid. That would go in the first box. What can you do to HBr? Yep. Right, those are aqueous. What do you do to aluminum bromide? Yep. And what do you do to H2O?
What is that?
That's a liquid.
It's not.
Yep, so that remains as H2O because it's not aqueous. It has a different phase than aqueous, so it still has to stay as a liquid. You can't split that up into ions there. So that stays at H2O liquid. So can anything cancel out? Your BRs will cancel. I think. Hold on, let me balance this real quick. BR. So the 3. It's 3, 3, 6, 3. Then you'll do this and this. Yeah. So then the bromines are the only ones that can cancel because those are the only thing that look like 3Br minus and 3Br minus. So those will cancel out. So then you're left with aluminum hydroxide, solid, 3H plus, aqueous. Aqueous and H2O.
So then, like the net ionic equation, I'm guessing, is that for D?
Yeah, that was for B. So I think what they want is the balanced equation would be this is right 1, I guess. Right, that would be 1. I think they want this in B. Where you have everything broken apart.
So they don't want us to mark out.
I don't think so. Technically, that's the full ionic equation, but I think for your homework situation, they're trying to look at all of that. I don't think they want you to leave it blank.
Okay, so the net ionic.
Oh, leave any extra answers blank. Yeah, so you cancel it out and you would just leave that one in red.
Okay.
Yeah, if you have extra, you can just leave it blank.
It doesn't matter what like specific blocks you leave blank, I guess, just.
Nope, just any extra that says blank. So, I mean, if I type this in here, I'll just try it for you. I have to do the rest of the questions in order for it to check it, but yeah, I think that should work out fine. Yep.
Thank you.
Yep.
So you break out like the ions when you're doing the ionic equation. How do you know if it doesn't like fully dissociate? Because I know he talked about the strong and weak. Does it always just dissociate or?
Yeah, so for the net ionic equations, I feel like we're mostly going to give you things that fully dissociate. When he's talking about strong and weak, he's looking at like molecular compounds and like strong acids or strong and weak acids. So something like HF, this is actually a weak acid, as in that doesn't fully associate. So it's actually equilibrium where H plus and F minus exist. So all 3 of those exist in solution. So even if like F minus appears on your left-hand side, it doesn't fully you can't cancel it out because they all exist at equilibrium or like at the final
So-
reaction. Yep. And you'll learn that like, if you were to cancel it out, then things happen in order to rebalance that equation. So you just leave all of them in the net ionic equation. Yep. Does that help? Cool. So I think like question C on this homework question is a weak acid. So you don't want to cancel those ions out because it's going to stay all three of those in solution. Like the one I have is HCN. So even though this is aqueous, it's in equilibrium. It's not in the equation, but it would be. And so you have CO, CN minus or CN3. But that's not going to fully dissociate into its counterparts. So you don't have to cancel it out.
Okay, wait, so, say it again, I'm so sorry.
Yep.
You're saying because it's weak, you don't cancel the terms that look the same on both sides?
Right.
Okay.
Because so HCN, right, it will actually have HCN go to H plus and CN minus. But it doesn't, it's not like only H plus and CN minus exist, right? When we think about, I'll write this differently. Right, this splits up into H plus and CN minus. When we think about NaCl, this breaks up into Na plus and Cl minus, and then NaCl no longer exists, right? It's only existing as its ions. Because HCN is a molecular compound, it's not ionic. It doesn't fully dissociate in water. Some of that HCN molecule still exists in water,
Because it's a molecular compound,
not an ionic compound,
Okay.
right? Electrons are being shared in HCN, electrons are being transferred in NaCl.
I see.
So, right, if we had HCN and we had a cup of water, right, as this goes in, we have H plus, we have CN minus, but we also have HCN molecules
So when they're covalent,
when they're covalent. Yep. If we had NaCl, this goes into water, we only have Na plus and Cl minus.
okay, so you can cancel when they're ionic, cannot when they're covalent.
Correct.
Okay.
Yep.
Okay.
Yeah.
Thank you.
Yeah, thank you. Have a nice rest of your week. Anything else? Like-
I'm like just learning because of like, we're doing things.
Yes.
Like, that's like stuff that I missed, I'm like picking up now.
Yes. I mean, that's why I kind of structure this the way that I do, because I think it's, you learn when you practice them. So hopefully that's helpful. It's 7:15, so people can leave, but that's it. An hour goes by so fast. But do you have any other questions? Feel free to ask them. If not, you're free to leave. I'm just going home, so. Yeah, thank you very much. Thanks for coming.
The girl who you continuously had to open assignments for, that's me.
No
Thank you so much.
problem.